Hello everyone, we are Team Swarm Robo from the Indian Institute of Technology, Roorkee. In this video, we are going to present the software model and simulations of our autonomous drone prototype. The complete model of the autonomous drone prototype can be divided into a number of subsystems. Going in a clockwise manner, first comes the structure and design, then the perception and vision, then there are planning algorithms, the control systems and the supporting auxiliary systems. Now coming to the first subsystem, that is the structure. In the structure, the frame is made by additive manufacturing, which provides the desired stiffness. Here are shown the different views of the prototype. The stand of the quadcopter will work as a creeping mechanism with no other actuation systems. Also, the ease of holding the payload in a non-constrained fashion makes it easy for loading and unloading. The assembly of the quadcopter is very easy for everyone. Now comes the structural analysis. The static structural analysis was conducted considering the conditions of flying. In addition to the static structural analysis, impact-based dynamic analysis was performed to study impact on model due to undesired scenarios. Coming to the next subsystem, that is the perception module. The perception is basically the vision segment. The simulation shows a gazebo model and an environment with ROS backend. The first segment of the perception module is the gate detection. This segment is significant as this algorithm gives us the gate's location and the reference point for the quadrotor to pass through. The gate detection algorithm was done by collecting images using the gazebo environment as well as the robot itself. The image shown on the right is a typical example of the image collected in the dataset. The complete dataset was annotated and was prepared by some HSV corrections and horizontal flippings. This helped us in multiplying the amount of images we have for training purposes. The object detector was trained using the ResNet 50 model and was post-processed for robust outputs. Now comes the most important segment of the perception module, that is the localization and mapping. In the video, it can be seen that the stereo image set are shown as well as the drone is rotating, generating the stereo images. These stereo images are combined with the extrinsic and intrinsic properties of the camera and the disparity map is generated. These disparity maps are used to create the depth map. Now, this shows a typical example of the localization and mapping framework that was used by the perception module. In the center, the stereo images are shown and the extracted features are labeled. These extracted features are used to get the disparity map, which is used to generate the depth map, which is shown in the top left. The top right shows the 3D occupancy grid, which is simplified as a 2D occupancy grid, which is shown in the bottom left. The bottom right shows the odometry data, which is used by the localization framework. This odometry data is purely based on the stereo geometry. Continuing to the next subsystem, that is the planning segment. In this segment, the complete model dynamics were considered and studied. The forces and torques on the body were studied by considering the dynamic thrust, the total drag on the body, and the total torque on the body frame. Accordingly, the equations of motions were formulated. The flight logic is based on a vertical takeoff and landing scheme. Also, the traveling between a point to the another in flight is based on an almost horizontal maneuver. The horizontal planning is based on a conformal spatiotemporal lattice which generates a set of feasible points or waypoints which can be chosen based on a cost function and which propagates the drone more towards the desired waypoint. The next segment is the control, which comprises of the controller, that is the complete flight control system. The motion planner supplies the reference waypoints and these are integrated with the sensor models, that is the estimated state. These are fed into the flight control system which actually commands the actuator to move in the environment. A generalized view of the flight control system is shown. The reference point and the estimated state is modeled as the position control for the attitude controller and the height control to the altitude controller. The yaw controller is based on the yaw direction that is needed to reach the reference points. Now, the outer loop position controller first generates the desired roll and pitch angles which are forwarded to the inner loop orientation controller which actually generates the roll and pitch torques. The yaw torque is generated by the yaw controller and the thrust is generated by the altitude controller. Thus, all these controllers give outputs which are fed directly into the motor mixing algorithm. This simulation shows a vertical takeoff simulation that was done in Gazebo. Now comes the next segment, that are the auxiliary systems. These auxiliary systems are composed of the connection module, which is the Bluetooth connection and the Wi-Fi connection. Such connections will help to connect with the ground control system as well as for interconnected drone activities. Next is the motor controller module. After the motor mixing algorithm generates the actuator commands, they are passed on to the motor controller module, which finally drives the motors. The internal ROS topics are always going on. These ROS topics consider the proper flags of the specific tasks. Next, the extended Kalman filter implementation and all these frequencies of the sensors should be organized such that there is no delay. Next is the battery management system. Now, the battery monitoring and the usage control is a significant segment when it is required for the drone to take long maneuvers. All these subsystems comprise the drone prototype that we developed. Thank you.